Welcome to Lesson 15. Here we're going to focus on calculating the heat for phase changes. The notes for this lesson go on the guided notes for the previous lesson, Lesson 14. Basically, we are going to work on solving word problems. For each word problem, or heat calculation, we are going to be using one of three formulas. These formulas are found on reference table T. Reference table T has to be used in conjunction with reference table B, as each equation has a constant found on reference table B. That constant is underlined here in red. It is either C, the specific heat capacity of water, H sub V, the heat of vaporization, or HF, the heat of fusion. Notice on the graph I've put where we're going to use these three constants. So when the temperature changes, we're going to use Q equals mc delta T. C, the specific heat capacity of water, is 4.18 joules per degree Kelvin. When the temperature is not changing at the plateaus where we have phase changes, we're going to use the heat of fusion, 334 joules per gram, or the heat of vaporization, 2,260 joules per gram. Notice the heat of vaporization is much larger than the heat of fusion. Therefore, it requires much more energy to break all intermolecular forces that hold a liquid together than it is to loosen the intermolecular forces between a solid and a liquid. Differences in kinetic and potential energy can be tracked using a phase change diagram. This is a special graph where the temperature, also known as the kinetic energy, is always the y. If the temperature is increasing, then there is an increase in kinetic energy. And if the temperature is decreasing, there is a decrease in kinetic energy. Potential energy, or stored energy, never changes while the kinetic energy changes. So if the kinetic energy is changing, potential energy will not. And if potential energy is changing, kinetic energy will not. When we look at these phase changes, we can have graphs that are endothermic. I know that this graph is an endothermic graph because the temperature is increasing from the start on the left to the end on the right. Notice that as we add heat, we slowly change phase. When the phase is changing, the potential energy is always constant. So as the solid is warming up, its potential energy is constant. The same is true for the liquid and the gas. So once you get to the phase change at the plateaus, you'll notice that instead of changing kinetic energy, notice how there is no change in the y value. We're going to change potential energy, the energy represented by the position of the particles. So in all of these changes, only one type of energy can change at a time. When the potential energy is changing, kinetic energy is constant. And when kinetic energy is changing, potential energy is constant. The same is true for an exothermic process. In this exothermic graph, I can tell it is exothermic because the starting temperature on the left is greater than the ending temperature on the right. This overall process is cooling down. Something cools down as it loses heat, or heat exits the system. The rule for only having one type of energy change at a time applies for all phase changes. So notice where we have the decrease in temperature, we have a constant potential energy. But when the potential energy is changing during the phase change, we have no change in kinetic energy. It is very important that you remember only one energy can change at a time. Looking at this endothermic phase change diagram one more time, we're going to talk about the conversion between solid and liquid. sometimes called melting, but always called fusion in chemistry. Here, the amount of heat added is called the heat of fusion. It's the amount of heat needed to melt 1 mole of a substance. Now, during phase changes, we have plateaus on the heating and cooling curves. That means we have no delta T. We will have to use a different formula. When reading word problems, we will know that we have to use a different formula when we see keywords like ice, freezing, melting, 0 degrees Celsius for water. Most of our calculations will involve water, or at constant temperature. Let's do this question together. Here we have the keyword melt. We also have 0 degrees Celsius. We have to remember that 0 degrees Celsius is a keyword here, and there is no temperature change. So as we set up our variable table, we see that we are looking for Q. We are given a mass of 35 grams, and recall that the heat of fusion of water is found on reference table B. Notice my calculator answer does not exactly match any of the answer choices, but it does match the rounded answer choice, choice 3. That is because choice 3 is written to the proper number of significant digits. Remember that when the temperature is not changing during a phase change between a solid and liquid, we are going to use the heat equation with the heat of fusion from reference table T. You will find the exact quantity for the heat of fusion for water on reference table B. If the substance is not water, they'll have to give you the heat of fusion, as this is different for every single substance. Now it is time to try one more question together. How much heat is needed to melt? See the keyword melt? 250 gram block of ice at 0 degrees Celsius. Remember, 0 degrees Celsius is also a keyword. When we substitute into this question and solve, we are going to find that we will produce 83,500 joules of heat. So the amount of heat absorbed is 83,500. Now it is your turn to try and calculate the heat required to melt 2 grams of ice at 0 degrees Celsius. One very important thing to note is heat is never 0. If you get an answer of 0, you need to try again. The final equation we will use is Q equals mHV. HV is one value, and it's the heat of vaporization of water. It is found on reference table B. Here, we're going to look for keywords like steam, boiling, condensation, 100 degrees Celsius, or a constant temperature. So here, in this question, you can see the keyword boil. We also have the keyword 100 degrees Celsius. So what we'll want to do is we'll want to set up a variable table. We have a mass of 43, and recall that HV is found on reference table B. All of these equations always have one variable either found on reference table B or given to us. Notice my calculator answer of 97,180 will be reported to 97,000 joules to the correct number of significant digits. So the next phase change we're going to discuss is between the liquid and the gas phase. The amount of heat applied to change the intermolecular forces between a liquid and gas is called the heat of vaporization. This value is also found on reference table B. So when solving problems where the temperature again is not changing, but we are changing a phase between a liquid and a gas, we are going to have to use the heat equation with the heat of vaporization. Remember, the heat of vaporization for water is on reference table B. If the substance is not water, you'll have to be given it in the question, as the heat of vaporization is different for every substance. Let's try this question. How many joules does it take to vaporize a 152.1 gram sample of water at 100 degrees Celsius? So here, the keywords are vaporize and 100 degrees Celsius. Now that we have our equation, we'll substitute. Remember, the value 2,260 comes from reference table B. Once we put this in our calculator, you can determine that 343,520 joules must be absorbed to change this amount of water into steam.
What is
Try
your
this
turn?
question. That concludes lesson 15,
of Unit 2.
Calculating heat for phase changes.